So good day guys, welcome to today's lesson. In today's lesson we are going to be designing the shear wall. Okay, so what we'll do is we can see most of our frames are passed. I'll just come back here, come to this show on deform shape, everything goes off. Okay, so it clears it. Now what I need to do is to select my shear wall, and the only way to select my shear wall is to come here, select object, or I can select the property type. So I can select wall, or I can come back here and select object type and select walls. Okay, so all the walls selected irrespective of the properties will be selected. Okay, so I've selected the right click and show selected objects only because it's just the shear wall I want to work with. So we can see our shear wall. First thing I need to do is to highlight everything, or if you don't want to highlight everything, if you want to select previously selected, you can come down here and you see PS or Ctrl G on your keyboard and to select the previous selection you made. So I'll come there. Now this is for shear wall. So in case if you don't see it, you can come to design and choose shear wall design. Okay, so you can see it. So I'll come here, it's faster here, and choose view revise override. So I need to set my parameters. So for example, I am using Eurocode. You can choose whichever code you want to use. We're using Eurocode. Now multi-response case design, so you can read all these things here, they will guide you. Now the rebar material, I created only one rebar, which is rebar 500. This is it. Then for the shear rebar, this is it. Now the country, I told you my default country, national annex, is the United Kingdom. Now we have various equations. If you remember my video on start where we did load combinations, where we had equation 6.10a and 6.10b, so you can change whichever one you want. Well, I'll just leave it at 6.10, okay, which is the most conservative. Now wall ductility type. Now like I told us that our current structure now is going to be a brace system, in the sense that the shear wall is the one resisting the lateral forces. So we have various types of wall ductility type. We have DC high, low, medium, and secondary. Now if I take secondary, it's going to assume that it's only gravity load. So if I've assumed my columns and beam are taking only gravity load, then I need to take my shear wall as a lateral system. So it's either I use high, medium, or low. So if you check your Eurocode, there are varying conditions for using this. But in a place like Nigeria, where the seismic is very low, is not high, so I'll use DC low. But if you are using a very special structure, then you use DC high. Then for a building with where you have high seismic system, high seismic effects in your country, and your building is high rise, then you can use DC medium or DC high. So I'll be using DC low for my shear wall. Now reliability class is mostly for the Danish and Finnish and Swedish national annex. So second order method in Eurocode, we are given to nominal curvature and nominal stiffness. So whichever one you want to use, you can select the one you want. So consider it. I'll select this, I'll select this. So now this is the gamma, material factor of safety for steel rebar 1.15, that is 15%. Then the for concrete is 50%, 1.5. Now the alpha CC is to reduce, this is for compression, this is for light concrete. So my utilization ratio must not go beyond 0.95. So I think I've set this to my taste. I will come back here again and define Pier sections now. So you can come here and define a Pier section. Let's say for example you didn't select auto Pier section, you can create here and add new Pier section, and you'll be doing it one by one. That's why I said let's do it automatically. So that's what we have. Now the thing with Pier is, let me explain the difference between a pier and a spandrel. Now a pier is this wall. So you, for example, now we have this height, this wall. Now from here to here, let's assume it is 3 meters, or it is 3 meters rather. Now since this is 3 meters, this will be 3 meters, this will be under 3 meters. So it's going to select a uniform wall with the same dimension. You can use the same pier for the same dimension. So for example, from this wall now, let's assume it is 3.5 or 2.5, it will have a different pier from this one. So that now spandrel is like the opening over the like a lintel. That was a spandrel, is like a lintel. So that is the concept of a spandrel. Okay, so we selected our walls. Let's go back there. Let's go to assign pier section. Now there are three different types of method of designing. We have the simplified compression and tension, and we have the uniform reinforcing. Now the uniform reinforcing is the one that just takes for flexure, and if it has compression, it will create a boundary for you. So let me explain what we mean in this in details. Okay, so let's take a typical shear wall. Now this is a typical plan of a shear wall. This is a plan. Okay, now this is the elevation of the shear wall. Let me draw the elevation of the shear wall. So I told you that the shear wall is a, sorry, let me see if I can stretch it down. So I told you that the shear wall is a long cantilever, right? So what it does is just, this base is fixed. So if you notice, for the foundation, I fixed the base to simplify the analysis, because if I pin it, then there will be more displacement. And you notice for the base, and the base of the shear wall, we always have a deeper footing for it. Okay, so I've done this. Now the next thing we need to do is, let me draw my lateral force. My lateral force is coming like this. This is the wind or the seismic. It comes at different flows, like I've shown you how it is. Now we have our gravity load also coming like this from this top. So when it comes like this, this is going to push the shear wall like this. The shear wall is going to tilt like this, something like this. Okay, so we've seen what we have now. Now this angle, this face, let me divide this. Let me divide this red one. Okay, 1 and 2. Okay, so this is going to be in tension, this will be in compression, then this will just be nominal reinforced or flexure. It just be like so. We have a tension column here and a compression column. You can see it that this is pulling away, this is compressing at this point, while this is pulling away, it is pulling away. So what we need to do is, this is the boundaries. So for example, if you've exceeded the concrete compressive strength, then you have to create a boundary for your wall. So let's go back to our ETABS and let's run our design. Okay, so we've created this. Now I'm going to choose uniform reinforcing first, because uniform reinforcing is the easier one. So uniform reinforcing, I'll select it. Then for example, now the thing which I wanted to explain in the addendum is that we can either check and design our reinforcement, but in this case I want to design it. So once I design it, I don't need to tamper with this. But if I check it, I need to set this. That means somebody has designed, I just want to check its provisions. But I want to design it, and I want to change this as my concrete grade. Okay, select this as my concrete grade. So I don't need to tamper with this because I know I'm designing to give me the area of steel. So I'll click OK. Now back again, select your walls, come back here and view override. So you set all this right. Now another thing is, you can change your pier section type from here to simplified C and T. So simplified C and T is what I explained here. So that is when you require a boundary reinforcement. So I will show you when you require a boundary reinforcement, if it really requires. So you can see the thickness of the bottom, the length, all of them varies. For now, I will go back to uniform reinforcing and select it to be designed. So click OK. So from there, I will just come back here and run my analysis. So once you click this, it will run, or you come here, start and design. But the good thing about ETABS is that ETABS will create automatic load combination. Now there's something, let's go back to this, sorry. Let's go back to this and let's look at we've created the load combination, so I think there is no problem. All other things, if I change it to red, it doesn't matter because it's just for this national annexes, so it doesn't matter. You can, so once I change anything, to change to red. So once I'm done with that, I'll just click this Shear Wall Design and it starts designing. So it might take a little while for it to run. So let's give it a little while. So it is done already. Now you can see the reinforcement has been placed already. So let's look at how to interpret the reinforcement. Select it, right click on it, so it brings out a calculation sheet, typical calculation sheet. So for example, let me make it 200. So we have this grade of concrete. You can see the typical everything. You've seen the height is 3 meters in the major axis, minor axis, the length, the thickness. So that's the length of the wall. So it has given you the centroid in the x and y direction. Now the Pier ID is PW5, so you can see it. So ductility class is low. Like I said, in Nigeria it is low. I don't know about your side, but if you want a medium, you put medium. I will check the difference between it now. So you can see the material factor which we've done. We've created this design code parameters. We've done this. Now this is the maximum reinforcement you can put, maximum percent, which is 4%. Then minimum you can put is 0.25%. Okay. So pier leg location and this, so like from the coordinates, these are the coordinates they've done for you. Now for the flexure design, we have NED, which is the axial load, ME2D, which is the bending moment in the minor direction, and ME3D is the bending moment in the major direction. So you can see for this, at the top and at the bottom, we have an area of steel of 1725 millimeters square, and this is the required reinforcement. This is what the code has said, the minimum you can get. So it is this. Then the current one, from the provisions we have, from the axial load and the moment we have, this is what is requiring. So we are placing the nominal according to the code. Now it has given us 1725. So let's go here. Let me explain what it is. Now the 1725, let me use another color. Let me use this color. So it is this, 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 this. This is the plan, right? Then this, 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 and this. Now we have total area of steel for this shear wall as 1725. So we have two faces. We have the near face and we have the far face. Okay. So for each of the faces, we need to divide this by 2. Okay. So 1725 divided by 2, that's 862.5. So this is the millimeter area of steel for each face. Now let's say, for example, now I want to use 12 mm. So and 12 mm, the area of steel for 12 mm is 113. So divided by 113, so that means I need 7.6, which is approximately 8. So that means in this face I need 8 pieces of 8H12, and in this place I also need 8H12. So that's the concept of it. Now if you want to get the spacing, you know this length is 3 meters. So if you remove cover, 25 from this place, 25 from this place, that is 50. Then you remove the stirrup, which is 10 mm, 10 mm, that is 70. So you have 3000 divided minus 70. So you are left with 2930 divided by 8 numbers. So the space is about 366. So you can just approximate it to 350. So you can see 12 at 350 center to center. So the good thing about Eurocode is that it allows 12 mm, 8 mm reinforcement rebar for it. So you can still use 8 mm if you want to reduce the spacing. Maybe you can use 8 at 300 center to center, or you can still come back here and make it minimum 12 at 300. There's no law stopping you as far as your provision is more than what is required. So for example, what is required now is 12 at 360. I can decide to provide 12 at 300 and CFA. So that's what we have. So let's go back to ETABS so we can understand it more. Now we are done with the flexure design. Now look at our shear design. It has given us this 230 millimeters square per meter. So for example, for every 1 meter, let's assume this is the 3. Let's just assume. Let me break it down. We know that this is from base to the roof, but let's assume this is from roof to the 15th floor and it's 3 meters. So you need to divide it into 3. That is per meter. So you can see this part here per meter. So we have 230. So we have 2 legs, which will be leg 1 and leg 2. Those are the 2 legs we have. So each of them from every 1 meter, 230 can be, maybe you just go to your steel table like a slab and check the spacing of it. So 230 can be maybe 10 at 250 or 10 at 300. You get it. But if you don't know, we have a value of 786 divided by spacing times area of steel will give you this value. So for example, I want to use 10 mm, and 10 mm is 10 times 10 divided by 4 times 3.14, which is 78.5. That's the area of steel for 10 mm, and our reinforcement here is 230, right? So we have 786 times 78.6, okay, divided by 230. So we can use a spacing of 10 at 250. It will suffice with our steel. So 10 at 250, 10 at 250 from top to bottom. That is just how to interpret it. But let's move on to other values. Let's see other shear wall. So we've seen the one at the top, the topmost part. Let's see the critical one at the bottom, and let's see what it requires. Okay. So let's pick this. Now we can see all this. You can see the height now. It has changed to 4 meters, and all other things I've explained today now. So you can see that we require 1.47%. That is what is required of this. Okay, 1.47% is what is required to work. So like I said, you can just pick. We have the top and the bottom, which is the bottom and the top. So you know it's a wall. So you just pick the most critical reinforcement. Maybe for example it is 11,052. So divide it by 2. Half of it will go to that side, half will come to the other side. Same with these two also. You can come here and get your this. So this is the concept of shear wall design. So we are done with this. You can check all other designs. Check all other. So what we'll do now is I will come here and select this. Now I want to display. So look at it. Display design info. Now I want to choose Pier reinforcing ratio. So you can just get the ratio of steel, select it. You can see 0.25%, 0.25%. But when I got here 1.6%, let me see here. This is 2.4%. This is very large. So you can see it's 2.4%. Okay. So next thing we need to do now is we can check identify all failures. So anything that fails will show us. So for now we don't have any failure because it is DC low. But in the next video we'll change it to DCI or DC medium so that I'll be able to explain that boundary condition for you. So thank you for watching today's video. If you have any question, you can drop it in the comment section. Thank you very much.